17.2, what we're going to do is we're going to continue with the idea of charges and positive and negative charges and repulsion and attraction. And this idea, this topic, okay, has to be understood to do further things that we're going to do later in the year. So remember how we looked at like equilibrium with forces, when we came to like pushes and pulls and friction. Now we're going to look at, instead of gravitational forces, we're going to look at the electric force. Now, if you have any inkling into like chemistry or material science, you like things that are like, you know, microscopic and whether you want to work with those, really important stuff here for sure. Because at a microscopic level, everything behaves differently. Okay, we traditionally in physics, mechanics especially, study everything on like, you know, the macroscopic level, the level we're on. But the minute things get much smaller in size, when we get atoms and molecules, suddenly the electric force plays a much greater role than the gravitational force. So we're going to be able to compare those two and take a look at their relative magnitudes, whether one is bigger than the other in certain instances. And we're also going to look to see how they're similar to one another. Okay, the idea of two particles being needed. Right? For gravity, you needed two objects. The formula was Fg equals gm1 m2 over r squared. That was our gravity formula that we learned about Newton's gravitational law. Well, in this section, you need also two particles. They have to be charged, and as a result, if they're charged, either they're attracted, if they're opposites, or if they're the same charge, they repel. But there's still going to be a force that exists in these cases. Let's start with first Coulomb's law. Okay, Coulomb's law. Coulomb's law tells us that the electric force, right, Fe, the electric force, is equal to some constant K, which we'll define in a moment, times Q1, Q2 over R squared. First, before you go any further, do you see how this is similar to the gravitational formula? The gravitational formula, if you forget, I'll write it at the bottom here so you can see. This was the formula for gravity. Now, as a result, what we can see is that we still need two particles, right? Two masses. What do you expect Q1 and Q2 might be? If we're looking again at the electric force between two charged particles, what do you think Q1 and Q2 might represent? Feel free to just take a guess. I can tell you it's not mass, obviously. But it has to do with two particles for this subscript of 1 and 2 again. What might they be?
Maybe like the speed? I don't know. Maybe like something like the way they...
Not the speed, but it's a property for sure, but not speed. If I had... Yeah.
The charge of each?
The charge of each of the particles. Very good, Marianne. Think about it. The only time a force of repulsion or attraction can exist due to electricity is if two objects are charged. If one is positive and one is negative, attraction. If they're both positive, repulsion. But you need a charge on each object. So in this formula, what we're going to see is the mass is irrelevant, because the mass only affects the gravitational force here. The electric force is based upon the charges of each of the particles. What was R in this formula for gravity?
The radius.
Not the radius.
The distance between the two centers.
Yes, the distance from center to center. Well, in this case, R is going to be the same thing. And what you'll notice, though, is that with protons and electrons, we don't have to worry about their radii being affected. Remember how with the planets we talked about that? Let me quickly remind you, a side note. If we had like, I don't know, a planet over here and then the moon out here, we didn't just calculate this distance, we also included the radius of each in order to get the distance from center to center. Okay, recall that from the gravitational part. We said it's like the radius plus this giant gap between the planets plus the radius. That was our distance we used in this formula. Well, in this formula, it's really defined as the same thing, but the radius of an electron or a proton is so minimal that it's negligible. So you're only going to hear about the distance between the proton and electron, or the distance between these two charged particles, whatever they may be. Maybe you have a sphere that's been induced with a charge due to induction, and then there's some other object over here. Well, you're just literally looking at the distances between them. When you use this formula a lot of the time, you're looking at microscopic levels. How is Kc similar in this formula? What do you see is the thing that's in this formula that's replacing it?
Well, Kc is kind of
Yeah, it's like G. And remember G, what was G? Anybody remember? Either what was it value or what is it physically?
Oh no, wasn't G a constant though?
It was a constant, good. It was a constant. Give me a more specific name.
Wasn't it the universal gravity?
Yeah, universal gravitational constant. And anybody remember its value?
Is it like 3.6 10 to the 11? Something like that? Or-
Something like that.
Okay.
Something like that. Hold on, let's see.
6.67 times 10 to the negative 11.
Yeah, 667, 10 to the negative 11.
3.6
Okay.
11.
Now, in this case, we have Kc defined as what's called the Coulomb constant. Coulomb is named after a French physicist who was a primary scientist in the field of electrical work. Okay, hence you're going to hear Coulomb's law, Coulomb charges are measured in coulombs. So it's called Coulomb's constant. Just like capital G, it will be given to you. You don't have to memorize it. It does not change. It is a constant. Right? A constant is something that isn't changing. Like G was 6.67 times 10 to the negative 11 for all of the universe. It doesn't change. Little g is a constant on Earth, the one that we know, 9.81. So capital or Kc, the Coulomb constant, is a constant throughout all situations, whether it be microscopic, macroscopic, things that are like planets in distance apart, like angstroms. So things that are really far apart from one another. Q is measured in coulombs. Okay, Q1 and Q2 up there. You want to jot down? Its units are coulombs. And R is obviously a distance, so it's meters. Okay, coulombs was the thing. Coulomb was the unit of charge. Like force's units are newtons. A coulomb is a unit of charge. Remember the other day we went over the electron charge is 1.6 times 10 to the negative 19 coulombs. That's the scientist who really came up with charged particles, or the idea. Just like newtons, right? 55 newtons comes after Newton. Newton is a force. Let's see, anything else? All right, let's go to the first example. Let's take a look at the first example. Using the table above, we want to find both the electric force between particles and the gravitational force between the particles. Those particles being an electron and a proton. They are separated in a hydrogen atom by a distance of 5.3 times 10 to the negative 11. So if you recall, a hydrogen atom, and we I think talked about this didn't we here? It is just a proton in the nucleus with an electron orbiting it. There's no neutron involved. So a hydrogen atom is simply a proton and an electron. So the question is, how does this hydrogen atom stay together? Right? How does it not want to repel? What's happening? So let's go ahead and figure out what the forces that exist between them are in this scenario. So if I want to find the gravitational force, I could use the formula for gravity. And you obviously should be able to do this by now because you've done it already. Okay, that's our formula. We know capital G, M1 and M2 are in the table. R is given in the problem itself. So we have everything. What could be tricky about these kinds of problems? What do you think could be tricky? Where could there be a bit of a hiccup along the way?
Well, multiplying and dividing in scientific notation.
Yeah, you're multiplying, dividing, you're squaring, all this stuff in scientific notation. So if you've struggled in the past in this, I encourage you to have your calculator out and be checking this right now. And generally, you should be. So let's go ahead and write in what we have for numbers. So we've got, I might have to make this a little smaller, hold on. We've got the following. 6.67 times 10 to the negative 11. Mass 1 is going to be 9.109 times 10 to the negative 31. That's the mass of an electron. The mass of a proton, 1.673 times 10 to the negative 27. That's a little bit messy. Hold on. It's a negative 27 as an exponent. You can barely see there. All over the distance between them squared. The distance between them was given, and that's squared. So there's a lot of room for error here. My recommendation, multiply the whole numerator, hit enter. Or multiply the whole numerator, and then hit divide, but make sure you put brackets around your bottom part. Because you have to divide by the whole quantity squared. You're not dividing by the quantity and then squaring it. So I would recommend putting a second set of parentheses around this. If you still use the 10, and you're not using the EE thing, you should really start to learn how to use that. And here's what I mean. Remember, 6.67 times 10 to the negative 11 on a calculator can be written like this. Right? Isn't that what it looks like on a calculator in blue there? Have you ever gotten an answer in scientific notation? There's always a little E there. Well, if you want to use that function in the calculator, press 6.67, then press second, and then I think it's a comma or an apostrophe. Am I right? Look at your calculator. Is it a comma or is it an apostrophe? A comma, okay. So press second after 6.67, press second and then hit the comma, and you'll bring up a capital E. Once that's up on your page or your screen, just press negative 11. Remember, the capital E replaces times 10 to them. There's no need to do that every time. It's more keystrokes. Save your time. All right. So typing this in, typing 9.109 times 10 to the negative 31, 1.637 times 10 to the negative 27 in the numerator, and then divide it by the denominator there.
Wait, it's 1.673, right?
1.673, yeah, times 10 to the negative 27. Notice, by the way, how much more massive a proton is than an electron? 10,000 times more massive. How do I know 10,000? Look at the difference in their exponents. How much does 31 and 27 differ by? How much? Right, 31 minus 27 is 4. So they differ by 4, and it's 10 to the 4, really? 10 to the 4 is 10,000. So a proton is about 10,000 times more massive than an electron. Okay, a lot more massive. What do we get as an answer here for the amount of gravitational force felt between these two? Jake, what do you got?
I got 1.9 times 10 to the negative 57.
1.9 times 10 to the negative 50. I got something different.
I got 3 times.
I got 3 for sure, yeah, but I got 3.6 when I did it.
Wait, you should put parentheses around your
Denominator?
factors in the numerator, right?
I mean, you don't really need to because they're multipliers. Well, you definitely forgot to square the denominator. You divide by
Oh, okay,
5.3.
that's probably what I meant.
So you need to take this answer from up here
Square.
and divide by this quantity, square, in parentheses. Sorry. What do we get as an answer? Somebody else? Mike.
I got 3.6 times 10 to the negative 47.
That's it, Mike. Very good. 3.6 times 10 to the negative 47. What are my units? What is it? Newtons. It's a force. The units are newtons. It's a force.
Oh, let's see again.
That'd be coulombs, yes, if it were charge we're looking for. All right, so a very, 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 very small amount of force, right? We're talking 46 zeros before we get to the 3 there. A insignificant, negligible, not needed force. Let's go to the electric force now, and let's do one of those examples. Same exact problem, okay? Same table. Now remembering the following, though. Here's the formula for electric force. By the way, notice what I do sometimes. Sometimes I put the Kc in front, like the G. Sometimes I put it in the top. It doesn't matter. I've seen that question, that mistake from a few of you. This K can go up top or in front. Either way, it's a multiplier. It doesn't make a difference. Traditionally, it's written in front because it's a constant. The constant is usually in front of whatever the expression is based upon. This expression is based upon charge, and distance. The constant is in the front. That's why sometimes you see it there. But I want you to understand that it doesn't really matter.
If the number is like so insignificant, then why does it even matter that we know it?
It doesn't. We're going to talk about it in a second, actually. That's a really good question. We're not going to care about it. Let's calculate FE first, and we'll see why we don't care about it. So Fe is the constant, right? Coulomb's constant, 9 times 10 to the 9, times the charge of an electron, negative 1.6 times 10 to the negative 19, times the charge on a proton, positive 1.6 times 10 to the negative 19, all over the distance between them, which is the same number as the last part, squared. So the only thing that changes here is the numerator. The denominator is the same because it's still a proton and an electron inside of a hydrogen atom. All right? So we don't have to worry about anything else changing. Go ahead and multiply these through. Divide by this number. You're going to get a negative answer. The negative answer is just going to indicate to you that it's an attractive force here. You could kind of, if you want to, really drop the negative here. Do all the work and then just write like 50 newtons of attraction. As long as you specify that because they're opposite signs, it is an attractive force. Still going to be a small number, by the way, but it's not going to be nearly as small as what you saw a moment ago. What do you got for a number for me? That's it. So again, still a very small amount of force. Extremely small. But relative to the gravitational force, this is 10 to the 39 times bigger. Think about it. 8 and 47, right? They differ by 39. So this is 10 to the 39, huge amount, times bigger than the gravitational force. So as a result, we consider the gravitational force at the molecular level insignificant or negligible. If you're doing calculations, if you're studying, I took a material science class in college, and what we would always do is look at things on a molecular or nanoscopic level, and we would have to calculate forces felt by different particles. We would consider that negligible, literally not even included. It would be like saying you have $50 million, and I come up to you and say, you want a penny? Would that help you save some money? Like, that has no significance whatsoever relative to $50 million, right? Same idea, except a lot more extreme here, actually. Okay, 50 million is a small number. We're talking, again, 10 to the 39. That's a 1 0 with 39 or 38 more zeros after it. It's a huge amount bigger. So, as a result, the electric force is the dominating force that exists between the electron and the proton to bind those two or to attract those two. Again, recognizing one more time that this negative sign that you're seeing in the answer simply indicates that it's an attractive force. I am more than happy if you do this. Watch. Make this a positive, and just put attractive. Okay, that works because in a minute we're going to do a few examples where everything's going to be positive. We're going to assume everything's positive even if they're negatives, and you'll see why. Okay, but as long as you know whether it's attractive or repulsive, I don't care if you forget or remember the negative here. You don't really need them here at all. You can just put the charge's magnitude here and then write the word attractive. Any questions on this one? All right, let's go to the next one. Now, before we start the next one, I want to go over what that symbol means, right? You see the mu? Everybody see mu there? Anybody remember what mu stood for, what prefix it was? What was the prefix for mu? What did it represent? For example, little m was milli, capital M is mega, little k is kilo, c is centi. What did that mu stand for? Anybody remember that one? It was on the table. This was like the beginning of the year. Okay. I'll tell you it was 10 to the negative 6. Anybody remember what that's called? 10 to the negative 3 is milli. 10 to the negative 9 is nano. What was 10 to the negative 6? What's the word for that?
Mega?
Not mega. Mega was capital M. That's 10 to the positive 6 is mega. It's called micro. Alright? So these are microcoulombs. So when you see a little mu, like 50 microcoulombs up there, you can write 50 times 10 to the negative 6 coulombs. Replace the mu with 10 to the negative 6. So let's start by listing our givens. We have a particle 1, 50 microcoulombs, which is 50 times 10 to the negative 6 coulombs. We've got particle 2, 40 microcoulombs, which is 40 times 10 to the negative 6 coulombs. We're told that there's a repulsive force. How do I know without even the word repulsive? I technically could have just done this. Okay, I could have read the word just force. How do I know it's repulsive, Kat?
Because they're both positive.
Yeah, they're both positive. They're both positive here. So I've got an electric repulsive force of 150 newtons. What am I trying to figure out? What variable am I trying to figure out? R, the distance between the two, R. I've got everything, so I can just plug in. Let's look at our formula. Our formula says this. Right, there's our formula. How do I solve for R? How do I solve for R? What do you got? Hannah, tell me, help me out. How do you solve for R in this case? What would I do?
You can multiply by R2.
Good. So multiplying by R squared, and then right after that, what do we do?
And then you can divide by that.
Good. So we can just technically flip these two. Very good, Hannah. Multiply by R squared, divide by FE, giving us R squared equals KCQ1 Q2 over FE. Remembering these numbers at the top, because they're going to run off the screen, okay? We can solve for R now by getting rid of the square by taking the square root. So there's our expression for R. All right, I just crossed off the square portion and put a radical on it. So you've got 9 times 10 to the 9 in the numerator, times 50 times 10 to the negative 6, times 40 times 10 to the negative 6, all divided by 150. And again, this is all square rooted. Go ahead and see what you get. Let's find that distance between these two particles. Can somebody also do me a favor? Convert 150 newtons to pounds. You could Google it if you want to convert it that way, or do it by hand, but convert 150 newtons to pounds also. I'm curious what kind of a number we're looking at here. What do you get for R? To the nearest, give me 2 decimals, hundredth, nearest hundredth. What do you get for R?
33 pounds.
That's what you get for pounds? Thank you.
34.
About 34 pounds?
0.7.
All right. What do you get for R? 0.35. And what are my units again? Meters. So, think about this for a second. These two charged particles are a third of a meter apart. It's about a foot. Okay? 3 feet is a yard. This is, I'm just estimating obviously, but about a foot. They're only this far apart. Yet they're exerting 34 pounds of force on each other, of repulsion. So, if I were to increase the amount of charge on each of these, what would happen to the force? If each of these were stronger, what would happen to the overall force? If Q's went up, what would happen to the overall force? What? Increase, because Q is in my numerator. The Q value is directly related to the amount of force. So these are not even that great amounts of force as magnitude-wise. Microcoulombs is not a large charge. Yet, even not a large charge, but a foot apart, presents you with 34 pounds of force. So the electric force is a very, very large magnitude force, relatively speaking, compared to the gravitational force. Okay, if you just look at the magnitudes, the electric force is a lot stronger than the gravitational force. Why do we care so much about gravity and less about electricity or electrical force for everyday life? Why is gravity more important than the electric force? For everyday life, forget microscopic stuff, for you guys. Why is it more important for gravity than the electric force?
Well, we have gravitational force, we don't have electric force.
Yeah, we're not charged particles, right? We're not like unbalanced. We don't have a ton of charge to ourselves and then an object is pulling us there. While we do have mass, and the Earth has mass, so gravity affects us a lot more than the electric force. Okay, but if we're looking at things that are charged particles, and a lot of things at the macroscopic level have some positive or negative charge to them, things change a lot. The gravitational force becomes much less significant, and the electric force becomes much more important. Okay? So let's make 3 before our last problem. The last problem is a lot tougher than the first 2 we just did. So those are the easy ones right there. 4 conclusions first. Can somebody explain the first one? What does the first one mean? It's a field force. So no contact, what does it mean by no contact? What can happen here? Kira? They don't have to touch one another. So these objects are at a distance from one another. We all saw the second bullet point in the analogous nature of the equations of gravity. Gm1 and 2 over r squared, k q1, q2 over r squared. Very similar in nature. The third bullet point we're recognizing is that it can be attractive or repulsive. Whereas gravity could only be attractive. Gravity can only pull 2 things together. It cannot push them apart. And then finally, in the last part, it's significantly stronger relative to gravitational force. All right. Last problem for the day is going to take us a little while. This is a complicated one. All right, give me your full attention for sure. All right, good. There's a lot of times. So take about 30 seconds. Read through it. Try and think about what a diagram of this would look like. Okay? Read through it on your own. Think about how you would draw a diagram representing these 3 particles. If you feel confident, draw yourself a diagram of where they would be relative to one another. Oh, this was prior to everything that happened. Just coincidentally. Oh man, I thought that was in response to. What do we have for the orientation of these 3 particles? How would they look if you were to draw a diagram? What would they look like? What do you got?
The third particle is all the way to the left.
Okay, so I'll put something over here.
And then...
Where do you want the next one?
And 0.2 meters to the right is the second particle. And then 0.3 meters to the right of that is the first particle.
Close. What mistake did Paul make there? Somebody help him out. So he was calling this particle 3, this particle 2, and this particle 1. It's literally flipped, the mirror image. Okay, it says that particle 1 is located 0.3 meters to the left of particle 2. So particle 1 and particle 3 should be reversed or just mirror image it. Okay, so this is what I'm seeing. Particle 1 is 0.3 meters to the left of particle 2. See what I'm saying, Paul? Okay. And then finally it says, and so particle 2, which is located 0.2 meters to the left of particle 3. So that's what you should see as a result here. Now, let's go further. We've got 3 particles. They're each charged differently. So we've got some force between 3 and 2, some force between 1 and 2, and some force between 3 and 1. You see what I'm saying here? 3 particles. So you have more than one force that's occurring here. Now, we want to consider the fact that the first particle is negatively charged, the second particle is positively charged, the third particle is negatively charged. So, think about this for a second. We've got a negative charge, a positive charge, and a negative charge. So, these two are attracting each other, aren't they? Opposite signs. These two are attracting each other. But these two are doing what? Repelling. So in the end, we've got this balance and this kind of like battle of forces. And the question presented to us is to determine the force on particle 3. On particle 3. So when you hear determine the force on an object, we need an FBD. So let's draw particle 3 by itself up here. Free body diagram. What did we say particle 3 feels from particle 2? What does particle 3 feel from particle 2? A pull. Good. So again, look, particle 2 is the opposite side of particle 3. So these are going to want to pull toward each other. So particle 3 literally feels a pull to the left. So draw an arrow to the left from Q3. It's being pulled by a force on particle 3 from particle 2. I'll point to that again. It's pulled by a force, here's my subscripts, on particle 3 from particle 2. If that is true, somebody tell me something about the other particle that affects particle 3. The other particle that affects particle 3. Marianne? Particle 1 repels it or pushes. And look, make sense of this. This is negative. This is negative. So these two, right, here and here, they want to push each other apart. So Q3 feels a push this way from Q1. So we'll draw an arrow to the right, showing that it feels a push to the right on particle 3 from particle 1. Now, we are only looking at the net force on particle 3 right now, right? That's only particle 3. You could do this for particle 2. You could do the same thing for particle 1. You could find the net force acting on all of these particles, and if you added all those net forces up, you'll get 0, because there's a balance of forces. But we are specifically finding the force on particle 3. Now, that means I need to calculate the electric force here and the electric force here. So if I want to calculate the electric force, I have to label these now. Q1 is -8 microcoulombs. Q2 was 3 microcoulombs. And Q3 was -4 microcoulombs. If I want to figure out what F32 is, for example, I don't need the negative signs anymore. When I multiply things now, I'm going to use Kc Q1 Q2 over R squared. Why don't I need to use the negative signs on the charges? Why don't I need it to be, for example, -8 microcoulombs? Why am I going to write just 8 microcoulombs?
Wait,
it's not being squared. Good idea, though. It's not being squared. That's exactly right. Very good, Kira. Remember with gravity, with little g, when we did forces, we called it 9.81 because the weight was already acting down in the diagram? Same thing happens here. We've already taken into account the negative positive signs based on the attraction or repulsion and the direction of those arrows at the top. Those arrows already took the negative signs into account. So as a result, for F32, I'm going to write the following. 9 times 10 to the 9 times particle 3, which is 4 times 10 to the -6 for micro, times particle 2, which is 3 times 10 to the -6, again for micro, all over 0.2 squared. Again, this here, you need to write it. This is Q3. This is Q2. So this is the force between particles 3 and 2. The distance between particles 3 and 2, where did this point 2 come from? Where? Yeah, look at the problem or your diagram. This distance between these two is 0.2. Between particles 3 and 2, so I take that distance, plug it in there, and I'm going to go ahead and square that. Alright? Now, if I were doing this for F31, I'm going to get an answer in a minute, but let's stay with the idea here. For F31, how would it be different? Look at the diagram at the top if you need to. Paul, give me something. Go ahead.
The distance would be 0.5.
Yeah, good starting point. Let's understand this first. Why is it 0.5, Paul?
Because you're adding both distances.
Yeah, look at the very top. If you look at the very top, the distance between this first particle, I'm pointing to it in case you're wondering, and the third particle is the sum of these two gaps. 0.3 and 0.2, the distance from here to here is indeed 0.5. Next, what other difference am I going to recognize? Yeah? Give me a minute. Yeah. What other difference will I recognize? This is still a constant, so it doesn't change. Now remember that in the last problem, this was really Q3, and this was really Q2, right? This was R, and this was KC in the formula. I didn't show it, though. How does it differ in this one?
Q1 is going to be -8.
Again, we're ignoring the negative, though, remember? We already took into account.
8 times 10 to the negative 6, and 4 times 10 to the negative 6.
Very good. So what we recognize, and if you look up, I'll point to it here, particle 3 is still involved. Focus, guys. Particle 3 is still involved. So if particle 3 is still involved, it still shows up, just like it showed up in the last one. But now it's not between particles 3 and 2. That was particle 2. This is between particles 3 and 1. So this is charge on particle 1. We need to calculate these numbers. I'm going to give you the numbers for the sake of time. F32 turns out to be 2.7 newtons. F31 turns out to be 1.2 newtons. Okay, we have 1.2 for F31 and 2.7. Well, the question becomes, what do we do with these numbers? Go back to your free body diagram. Look at it. F31 is positive force, a push to the right. F32 is a negative force, a push to the left. So as a result, we can take whatever F31 is, the positive one, whoops, and subtract F32 from it. So let's go ahead and look at that. We've got this positive F31, which is to the right. And we've got this F32 to the left. That's going to be a negative. So as a result, if I want to find the net force, okay, if I'm looking for the net force, I've got, again, a positive 1.2 newtons over here, a negative 2.7 newtons over here. So the free body diagram is what gives me the negative sign. That's why I'm telling you to drop the negatives. Please, again, drop the negatives in the equation. And then as a result, we can take 1.2 plus negative 2.7. That's going to be the overall force of negative 1.5 newtons. So we could summarize this by saying that particle 3 feels an overall pull to the left because it's negative. Sure, particle 1 pushes it to the right, particle 2 pulls it to the left, but particle 2, its pull to the left, is stronger than particle 3's push to the right. Or particle 1's push to the right. So as a result, this negative 2.7 overcomes the positive 1.2, yielding negative 1.5 to the left. I simply added those numbers together. In case those of you are wondering, because I saw a blank look or two. Okay, add these two values together to give you the final answer. Over the weekend, is 3 problems to try. The problems might take you a little while. Don't give up on them, though, please. Please don't give up on them.